Hello class. In this video we're going to cover Unit 4-1 where we introduce the Laplace transform. So to give you a little bit of background, um, the Laplace transform is a great way to solve some linear differential equations because what it allows you to do is to turn a differential equation into a algebraic equation. And the nice thing about algebraic equations, is that you can solve them pretty readily, I think. We've been solving them for a long time in our lives. So, well, let's jump right in. I want to introduce an analogous process to kind of show you at least the utility, if not the motivation, for why we would want to switch from differential equations into algebra. And so let's pretend that you wanted to multiply Roman numerals. Well, and you can see I provide you a table of Roman numerals here. If you wanted to multiply Roman numerals, think about the process you would have to go through here to solve this. Well, we have x II times IV, right? And so if you think about what these numbers are in your head, maybe you know, maybe you look at peek at the chart here, but in reality, what we're talking about is 12 times 4, right? Well, that's 48, that much we know. And then we peek back at the chart to give us our answer in Roman numerals. And so we look at 48, it's XLV triple I. And so think about the process that we did here. Well, we had to first convert 12 back to to Arabic numerals, just like the number 4. So then what we had to do was to actually multiply them out. So then multiply. Then after that, we had to convert our answer back to Roman numerals. And so this is exactly the process that the Laplace transform is going to take. So we're going to start with a problem that is a differential equation. So let's pretend that that's analogous to our Roman numerals. We are going to use something called the Laplace transform to convert it to an algebraic equation, which is going to be played by Arabic numerals here, right? And then we're going to get an answer, which we then transform back via what's known as the inverse Laplace transform, back to the answer to the differential equation that we're looking for. And so we're going to develop that process slowly, but first we need to talk about what the Laplace transform is, and that's what units 4.1 and 4.2 do for us. But here's just a taste of how that's going to work. So we have a differential equation here. Now this one is not very hard to solve. Y prime plus 5y equals 0 with y of 0 equals 2. But what we're going to do is we're going to essentially use the Laplace transform to help us solve this. And then I'll show that what we get is actually the same answer that we expect to get. Okay. So I have a table of Laplace transforms down here. So if you see L of, let's say, little y, then the Laplace transform of that is going to be capital Y. And now the variable switches from t to s. Okay. And if we look at L of y prime, then, well, we get the Laplace transform here. So whatever the Laplace transform is doing, it's doing this. So it's s times capital Y of s minus little y of 0. Okay. All right, so what we're going to do is we're going to take our differential equation right here and transform it via the Laplace transform. And what we'll see is that we'll get an algebraic equation. Okay, so let's just do that right here. Now, So what we're going to do is we're going to take the Laplace transform, which is the script L of both sides. Okay, so the first thing we're going to remark is that L of 0 is just 0, so it sends 0 to 0. So on the right-hand side, we just get 0, okay? But on the left-hand side, it turns out the Laplace transform, which we'll see in the next unit, Unit 4.2, we're going to see that it's linear. So let's just pretend we have that fact for now. So linear means I can split at plus and minus signs. And linear also means that I can factor out multiplicative constants. So I get L y prime plus 5L of y equals 0. And that's this remark right here, right? So this is essentially what linearity gives us. And now L of y prime, I know what that is. That is S times capital Y of S minus little y of 0 plus 5 times, now L of y, that's capital Y of S. All right, so this is an algebraic equation. Notice there are no derivatives. I just have a single variable, and y is just a function of that variable. So this is indeed an algebraic equation. So let's turn the page and solve this algebraic equation for y of s. So let's rewrite it here. So I get s times y of s minus 2. Notice y of 0 is 2 by assumption. So let's make sure we see that right here. Right? So y of 0 is 2. So I'm just going to replace it right there. So I get s times y of s minus 2 plus 5 times y of s equals 0. You'll notice I can add the 2 to both sides and then factor out y of s. So I get capital Y of s times s plus 5 equals 2. And now capital Y of s equals 2 over s plus 5. And in the very next part here, we solve for y of t by taking the inverse Laplace transform that I told you earlier about. So y of t is the inverse, whatever that means, the inverse Laplace of this expression right here, 2 over s plus 5. And now let's look back to our table of Laplace transforms. So do we see anything that matches that? Number divided by s plus a number. Well, let's just go through here. So we're looking in this column, and then inverse Laplace transform is the left column. So let's see. Well, I would say that this one actually looks closest, right? We have a number 2 in our problem, and then divided by s plus a number, whereas this says s minus. Oh, but that's no big deal, because plus is just double negative, right? So this is actually the Laplace inverse of 2 over s minus negative 5, right? And now let's go back to that table. So c is going to be 2, so my inverse Laplace transform is 2 times e to the minus 5t. Okay, so we're going to claim that that is our answer. And now let's check it against methods that we already know how to do. So y prime plus 5y equals 0 with initial condition y of 0 equals 2. Well, this can be solved, I think, via separation of variables. Notice this is dy dt equals minus 5y if I just subtract 5y from both sides. You could also use reverse product rule, but I think this is going to be quicker. So we get dy over y equals minus 5 dt. So ln absolute y equals minus 5t plus c. And now we exponentiate. And so when we exponentiate, we get y over here, and we get e to the minus 5t plus c here. But that's e to the minus 5t times e to the c. And now remember, we call this just a new constant. So this is c e to the minus 5t. So we're in good shape. Now we just need to check that c is equal to 2, right? Well, y of 0 equals 2, but that is c times e to the 0, which is c. So c is 2. And so y equals 2e to the minus 5t. And that checks, right? That's exactly what we got up here by using the Laplace transform. So you see the amount of work, if you actually look at the amount of writing that we did, roughly the same. It's just that now we have another avenue to solve linear differential equations. And so for a summary of what this process is, let's come to the 4th page of Unit 4.1. This is essentially what we did. So we started with a differential equation, y prime plus 5y. We converted it using the Laplace transform to this algebraic equation, sy of s minus 2 plus 5y of s equals 0. We solved it, and then took the Laplace transform back to get our answer to the original differential equation. And so that's what this arrow is representing here, that this little y of t solves this differential equation right here. So we went this direction, whereas the methods we've learned before, there's a lot of steps, but they're this, going this direction. So as we move forward, we're going to see some unique properties of the Laplace transform and some of its utility as well.